Hi folks, Mrs. Allen here, and we are studying 7.2 areas in the plane. And so we just came off looking at accumulation functions, Riemann sums as they carry over to integral expressions. And so we're looking at area between two curves. So you'll be able to apply the definite integral to solve problems involving areas between limits of Riemann sums, areas between curves, and areas for which integration is with respect to y instead of x. You'll be dealing with what we call horizontal rectangles then. So the first step, we want to partition the region from x is equal to a to b with strips of equal length delta x, you can see. So when we give it an area like you have in the first picture, we have a top and a bottom function, and that image where you have it shaded from a to b between the two functions f and g, that gives us the exact area. So we can partition then n rectangles, and so if we do, that gives us an estimate or an approximate area in the middle diagram. In the last diagram, we have a representative strip, the rectangle with area a sub k. And so we often take one of these, like taking a rectangle out of this middle diagram and saying this is our representative rectangle. That will help you to be able to formulate the area expression. In this case, it would be a sub k is equal to, well, kind of what you see above here, this section. It'll be equal to this, or better yet, here's a sub k, and it's utilized in the summation. So when we come down here, the limit as x approaches 0 is the limit as n goes to infinity now for this expression, the summation from 1 to n. K is equal to 1 to n of f of x sub k minus g of x sub k delta x, which is equal to then the integral in the last part of this from a to b of f of x minus g of x dx for that, okay? So it's going to be important to see what the top function is and what the bottom function is. And then very often what I would sometimes do is draw a vertical line just to see that's the top, it's always the top, that's the bottom, it's always the bottom. But many other times to get used to it, remember that this rectangle, even though it looks kind of thin there, has a thickness of delta x. So then we have the definition of the area between curves here. So there it is. And we have that last expression where it's the integral from a to b of f of x minus g of x, as long as f of x is greater than g of x on the interval from a to b. That gives you the area then. It's talking about area. And then if we look at this, find the area of the region between y is equal to secant squared and y is equal to sine x from 0 to pi over 4, where 0 is a and b is pi over 4. So think about what is the top function minus the bottom function, and it's labeled here for you. Sometimes you have to know that or graph it. So we have the integral from the top minus the bottom from a to b. A is equal to pi over is equal to 0 and b is equal to pi over 4. So then we set it up, the integral from secant squared minus sine x from 0 to pi over 4. And then we'll take the antiderivative of secant squared, which is tan x, and the antiderivative of minus sine x, which is positive cosine x. Sometimes you want to do a think cycle, if you will, when you're going to have to find out what is the antiderivative of sine x. And sometimes it's that sine, S-I-G-N, that students will get messed up. So remember, if I find the antiderivative of sine, that term, whatever it is, if I take the derivative, I have to get a positive sign. So it's got to be negative cosine. So then finishing this, evaluating, and you get an answer of the area is square root of 2 over 2. So the area is equal to root 2 over 2. Okay, now we did go over this. I just want to make sure that if there are any questions, you have them answered. So give you a chance to look at what we did in case you missed any lines of the problem. Let's move on to example 2 with area. Find the area of the region enclosed by the parabola. Y is equal to 2 minus x squared, and the line y is equal to negative x. So remember with this that you had to say, okay, what if we didn't have a graph of this? I'm giving the graph so that we can expedite the process of working through the problem with the important details. So we have points of intersection that we sometimes have to find. So that means you just solve a system, set the two equations equal to each other. If you're doing it by hand, generally the answers are integers for the x values. They're not too awful. On the AP exam. So if you have the x values, then you have x is equal to 2 and y is equal to negative 1. Now, as it turns out, in one of the classes we solved for what the y value was, but in this case, we don't want to know what the y values are. So if I call that y2 and y1, we're not going to need the y values for this. All we need are the x values to get the interval of integration. So you can picture that that rectangle move left and right, where the top is the top and the bottom is the bottom, all the way through there, okay? Through the interval from -1 to 2. So first thing we did is we find the area sub k of one strip. You can see that its width is delta x. As it meets along the x-axis, you can kind of see it's showing that width of delta x. And then the height of that is 2 minus x squared minus the negative, right here, 2 minus x squared minus a negative x. So now what I did is I had that put up here for the area. There's our area sub k of that representative strip, and then that will help us to write the actual integral. Now what I did in the next two lines is I simplified it, okay? So I'm going to take that last expression, I'm going to put that into the integral down here, and then I put the intervals of integration from -1 to 2. Now keep in mind, we already have our, what we consider to be our f of x minus g of x is already up here. So all I did was simplify it. I'm just putting the expression 2 plus x minus x squared in. Now, we're going to evaluate that then once we take the antiderivative in step 4. We evaluate that from -1 to 2. So I think I'm leaving that for the reader at this point, and you should get 9/2 for an answer then, okay? Double check it, do a quick estimate. You can use a triangle if you want to for area of some sort. Sometimes you use a square, sometimes a rectangle. Okay, let's look at the next one, example 3. Example 3, the thing that I liked about this is it presented a way that we could quickly use technology and reason about this particular function as being an even function. Both functions being even, you have y-axis symmetry. So even and odd functions give you the availability of shortcutting your process. So we can see which one's on the top. So we have the top function up here, 2 cosine x, and then the bottom function down here, bottom function is x squared minus 1. So in this we have the 2 cosine x minus the x squared minus 1 dx, okay? Then we've got to find out what a and b are. The problem with it is that we have two functions that aren't going to solve nicely like polynomials, so we have to use the graphing calculator for this. And let me see, we have our answer here, and I know it's kind of messy here looking at it as I review this. So if I have to find these, remember, you're going to put these in a calculator, and then you're going to do this second calc 5, right? So you do the second trace 5 for intersection, and I think you guys know how to do that. So it turns out that you get point A, and then point B in your calculator for, and then you notice and you go, oh yeah, right? Oh yeah, that in this case, we know that they should be the same y value, and the x's are going to just be opposites because we have y-axis symmetry, or we have two even functions. So with this, as you go through this, if I have a value like this, first thing off is I can store it. So I'm going to type in the number, or if you've already calculated it, you can just go ahead and hit the stow key right after you calculate it. It's in the enter column, and then hit stow alpha A, and then you're going to hit enter again. Okay, so you hit enter after that. So now what you've done is you've told your calculator to store that number in A. So every time you hit A, I think what we did in class is we took it and we multiplied it by 2 and we got 2.53 something, right? So just to check that, oh yeah, every time I hit A, I'm going to get 1.26542, blah, 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 blah. And so we doubled it and we got the answer that we expected, 2.53. Anyhow, so what you can do then is that when you type this in, so you said it was even, and you said, okay, see, everything is about efficiency and understanding. You want to understand what's going on, but you want to do it as quickly as you can. You don't want to waste time. You've already typed in your functions into the calculator, y1 and y2, right? So you did this, and I think we were talking about it, so let me highlight that as well. So you did this, y1 is equal to 2 cosine x, and then you said y2 is equal to x squared minus 1. You viewed them and you decided which one was on the top and which one was on the bottom and so forth. So you knew how to put them in. So first you want to look at the graphs, right? You want to find the points of intersection. So you've already got them in the calculator. So then at that point, I'm going to go back to the home screen and I'm going to hit Math 9. And when I hit Math 9, I'm going to hit a 2 first, and then I'm going to go here to the 2, I'm going to hit Math 9, and then I'm going to type in 0, and then I'm going to type in alpha B to get the B in, because, oh, wait, wherever you store, I think I said A down here, but say we stored that in B, but we want that second coordinate. So I'm going to go from 0 to b, and then I want to type in the y1 minus y2. And recall that the way you type this in, you've already done Math 9, you're on your home screen, and you're looking at this. So really, these aren't in there yet. So to get them, you're going to hit alpha, trace, 1, and then you get the y1 pop. Okay, you're going to put the minus sign in, and then for this one, you're going to hit alpha, trace, and then you're going to hit 2. So, and then you're going to do alpha, trace, 2. And then you get this, y2. And then you're just going to type in the x here. So now you have your integral done. You don't have to type your entire function in. Again, you have it there, and you get your answer, 4.995, because you look at your original and you round to 3 decimal digits, okay? So lots of calculator things that are going to be efficient for you. And this is definitely a calc problem. Go TI-84 or the TI Inspire or any graphing calculator. Thanks for your help. All right, example 4, finding areas using subregions. Okay, in this one, what we did is that we found the area of the region in the first quadrant that is bounded above by y is equal to the square root of x and below by the x-axis, and the line y is equal to x minus 2. So you had to have a little knowledge of functions here. And if you recall, we drew the square root of x, which is the red graph, and then we drew x minus 2, which is the blue graph. We found out that they intersected at the point 4, 2. So now what I did on the left and the right, I split the areas because I noted that on the left-hand side of that vertical line I just drew it to, that the representative rectangle had a top that was on the square root of x, but the bottom was y is equal to 0. And then for the other part, it looks kind of like a triangle, is really the top is the square root of x, but the bottom turned out to be the line x minus 2. So you can see that I came up with the 2 representative areas there. On the interval from 0 to 2, it looked like the area sub k was going to be square root of xk minus 0 delta xk. And then the area sub I for the purple one is a sub I is equal to the square root of x sub I minus xi minus 2. X sub I minus 2 delta x sub I. And that's on the interval from 2 to 4. So then, here, let me put this down here because this would be from 2 to 4 here. So from 0 to 2, we had that first integral, okay? For the area total. This is area total. I have 2 integrals. So I go from 0 to 2, the integral of square root of x minus 0, and then from 2 to 4, the integral from 2 to 4 of square root of x minus the quantity x minus 2. Simplifying a little bit, and then again, these integrals are fairly easy, so I'm going to leave it to you guys. It turns out to be 10/3 for the area. Make sure that you can do this by hand later on. You don't want to get lost in the shuffle, not remembering how to do integration. So the integrals generally are pretty easy to handle manually by hand, but setting them up is the part that you have to analyze and figure out how you're going to write this integral. And that area sub I, area sub k, setting up that area for the rectangle helps out tremendously.